A simplified model of a mixture involving gases and a vapor. Let us now consider a simplification, which is often a reasonable one, of the problem involving a mixture of ideal gases in contact with the solid or liquid phase of one of the components. The most familiar example is a mixture of air and water. Mixture of ideal gas. And that is in contact with a solid or liquid phase of one of the components. The most familiar example is a mixture of air and water vapor in contact with liquid water or ice. For example, a mixture of air and water vapor in contact with liquid water or ice. Such as in air conditioning or in drying. We are all familiar with the condensation of water from the atmosphere when it cools on a summer day. This problem and a number of similar problems can be analyzed quite simply and with considerable accuracy if the following assumptions are made. The assumptions are: 1. The solid or liquid phase contains no dissolved gases. The gaseous phase can be treated as a mixture of ideal gases. Can be treated as a mixture of ideal gases. When the mixture and condenses on the last assumption, or at a given pressure and temperature, the equilibrium between the condensate phase and its vapor is not influenced by the presence of other components. Between the condensate phase and its vapor is not influenced by the presence of other components. This means that when equilibrium is achieved, the partial pressure of vapor will be equal to the partial pressure of the vapor will be equal to the saturation pressure corresponding to the temperature of the mixture. Temperature of Since this approach is used extensively and with considerable accuracy, let us give some attention to terms that have been defined and the type of problems for which this approach is valid and relevant. In our discussion, we will refer to this as a gas-vapor mixture. In this case, we have a definition for dew point. The dew point of gas-vapor mixture is the temperature at which the vapor condenses or solidifies. When it could which is cooled at constant pressure. This is shown on TS diagram for the vapor shown in this picture. TS diagram, P constant and T constant process, V constant process. Suppose that the temperature of the gases mixture and the partial pressure of the vapor in the mixture are such that the vapor is initially superheated at state 1. If the mixture is cooled at constant pressure, the partial pressure of the vapor remains constant until point 2. Saturated vapor. We have a pressure constant process here. P const. So the temperature as a state 2, T equals to the dew temperature, dew point. Lines 1, 2, 3 on the diagram indicate that if the mixture is cooled at the constant volume, the condensation begins at point 3, which is slightly lower than the dew point temperature. If the vapor is at the saturation pressure and the temperature, the mixture is referred to as a saturated mixture. If the mixture vapor is at pressure and temperature, saturation pressure and temperature. Pressure and temperature, the mixture is referred to saturated mixture. And for an air-water vapor mixture, the term saturated is used. For air-water mixture, saturated air. The relative humidity Phi is defined as the ratio of the mole fraction of the vapor in the mixture to the mole fraction mole fraction of the vapor in the mixture, 2 mole fraction of vapor in a saturated mixture. At the same temperature and total pressure. Total pressure, since the vapor is considered an ideal gas, the definition reduces to the ratio of the partial pressure of the vapor as exists in the mixture PV partial pressure of the vapor the saturation pressure of the vapor as it exists in the picture PG, PV and PG. So humidity, relative humidity can be written as this expression. In terms of numbers on TS diagrams of the picture here, the TS diagram, V equals to PV on PG or P1 on P4. Since are considering the vapor to be an ideal gas, the relative humidity can also be defined in terms of a specific volume or density. So can be write PV, PG, rho V on rho G, the humidity ratio omega of an air-water vapor mixture is defined as the ratio of the mass of vapor m v to the mass of dry water air-water, defined as the ratio of the mass of the water vapor mv to the mass of the dry air water. PMA, or we can write omega equals to humidity ratio MV on MA. The term dry air is used to emphasize that the humidity are used synonymously with the humidity ratio. The dry air is used to emphasize that this refers only to air and not to the water vapor. The terms specific humidity or absolute humidity are used synonymously with the humidity or specific humidity. Absolute humidity or humidity ratio. MV on MA. This definition is identical for any other gas-vapor mixture, and the subscript A refers to the gas. For any other gas-vapor mixture, instead of air vapor, MA refers to the gas exclusive of the vapor, since we consider both the vapor of the mixture to be ideal gases. A very useful expression for humidity ratio in terms of partial pressure and the molecular masses can be developed as this relation MV PV VMV PAV RAT PVV RVT PAV RAT RA on PV RV on P A MV PV MA PA, air and vapor. For an air-water vapor mixture, water mixture, we have this relation omega phi pg p total minus PV. The degree of saturation is defined as of the ratio of the actual humidity ratio to the humidity ratio, the actual of a saturated mixture humidity ratio of saturated mixture at the same pressure and temperature. This refers to the maximum amount of water that can be contained in moist water. Refers to the maximum amount of water that can be contained in moist air. Which is seen from the absolute humidity equation. It is P PV. Since the partial pressure for the air PA equals to P total PV and PV equals to PPG, omega equals to The maximum humidity ratio corresponds to a relative humidity of 100%. Maximum %, and is function of the total pressure and temperature due to Pg. Function of total pressure and the temperature due to Pg. This relation is also illustrated in the picture provided here as a function of temperature. As a function of temperature, this picture, and the function has an asymptote region or state not permissible, as the water vapor pressure would be larger than the shaded region or state not permissible, as the water vapor pressure would be larger than the saturated pressure. In a cooling process at constant total pressure, the partial pressure of the vapor remains constant until the dew point is reached at 2. This is also the maximum humidity ratio curve. Further cooling lowers the maximum possible humidity ratio and some of the vapor condenses. The vapor that remains in the mixture is always saturated and the liquid or solid is in equilibrium with it. For example, when the temperature is reduced to T3, the vapor in the mixture is at state 3 and its partial pressure Pg at T3, and the liquid is at the state 5 in equilibrium with vapor.